accidents that kept me and my wife from attending this meeting, and I've decided to have a discussion in our seminar room in a very informal atmosphere. Actually, in this room that Ulf Meissner and also Andreas Wirtzba were students, so it's quite appropriate. Now, I call this Conducting Hans Bethe Down the Path to Nothingness, that is, black holes, because this was the work that he did later in his life. Actually, we wrote together a book called Evolution and Formation of Black Holes in the Galaxy, which has 21 papers in it, which were produced in the 21 years that we worked together, roughly one paper per year. So, and in fact, he helped me edit this book when he was 93 years old, in that he checked all of the commentaries and in general gave his opinion on all of the subjects. Now, I want to, first of all, here's the book, Formation and Evolution of Black Holes in the Galaxy, and we dedicate this collection of papers to Rose Bethe, who throughout their long evolution led us, counseled us, and cheered us on. So I want to go back. I want to go back to 1978, when Hans came to Copenhagen, where I was professor in the Bohr Institute. I'd been to his retirement party in Ithaca and actually suggested that he come and work with me in Copenhagen after his retirement. In fact, I met the Bethes many years before in Birmingham, where I was a postdoc, and with Rudy Peierls, who is probably his best friend. So on their way, they came from Israel to Copenhagen, and on their way they stopped in Turkey in order to make a hike. And they made the hike on Mount Pion. Now actually in Turkish it's called Mount Pion, but I called it Mount Pion because he had sprained his ankle on climbing the mountain and was hobbling in to Copenhagen, where we picked him up at the airport, and he met them. We took them to their digs, and then he asked me, what are we going to do? So I said, well, we won't, you've been working on pions, and obviously the gods are not with you, because every higher order that you evaluated gave new contributions which were just as large as every lowest or lower order put together. So the gods are telling you that you should not work anymore on pions. So then he said, well, what should we do? And I said, well, I've been working on the collapse of large stars, and I think we should work out that problem. He said, I don't know anything about it. I said, well, I know that they have a lot of the nuclear physics wrong, but what I need is an expert on explosions. And he admitted to be an expert on explosions because he had headed the theoretical group at Los Alamos that built the atomic bomb during the war. So actually, I left printout from Woosley about a star that was just ready to explode on his desk. We'd taken them to their digs, and he took the bus in the morning to the Institute. Actually was there when I arrived, and I went down to his office, and he said, "You know, the entropy is very low." And I said, "Well, what does that mean?" He said, "Well, there's only entropy of 1, that is in Boltzmann's constant, per iron atom, and that means that there's not enough entropy for the iron atoms to break up as they fall in." Now, in fact, at that time, everybody who had calculated the supernova problem had found that iron, or whatever they had, only went to about 1/100th of nuclear matter density and then stopped. So I said to him, "But this is not at all like what people had obtained in their calculations." And he said, "They're wrong." And it turned out that, in fact, they were wrong, and we could show that when the problem was handled properly, that the inner core actually came down to more than nuclear matter density before it bounced, because if the iron nuclei are together, then the entropy in terms of Boltzmann's constant per particle is only kT, or you call it tau in the trade, and that's for the whole iron nucleus of 56 particles. Whereas if iron were to break up, you would need much more entropy. You would need something like an additional log of 56, since those things go in logs. And you don't have that much entropy. So this is a sort of calculation that he had done of the entropy, and you see that, well, that just, I'm going to, by and large, show a number of the calculations, but so we actually, within the first month, had solved the problem of the stars going to a very high density in the collapse, and then I thought that all of the problems would be that easy. So we went along for some time, and we actually had solved the problem of collapse in that spring. There was a meeting later on, and pretty well everybody had accepted our solution of that problem. But then I thought, well, this is an easy problem, and we should be able to solve the supernova problem in no time. Well, then we worked at the supernova problem, and worked, and lots of other people worked, and everybody ran into difficulties. Well, Hans and I, after that first year, used to get together every year for a month or so, and normally we went to the West Coast where the weather was nice, and the relevant university, mostly Caltech, but earlier on Santa Cruz and other universities, lent us an apartment, and we could work at the institutes. And we left our wives at home because his wife had her parents to take care of, and my wife had the children to take care of, and so we went alone, and he liked home-cooked meals, so I went shopping, and I'm a pretty good cook, so I made the home-cooked meals. And then we had long breakfasts together and talked about what we were going to do during the day. After that, we would go into the university where they had given us an office, and he took out his slide rule, and I took out my $16 computer. By lunchtime, we had generally had a good start on the problem that we were working on, and then by tea time we usually had finished the calculation that we had set out at breakfast and went home and discussed it, and then I made supper. So none of the explosions worked, but then in 1987 we actually gave up working on the supernova because we didn't have any new ideas, and we said, okay, let's work on relativistic heavy ion physics. And we worked somewhat on the relativistic heavy ion physics, and when I went home from him, I shook his hands and said, okay, Hans, now it's time for a supernova. Well, in February there was a supernova. So 1987A, and then we thought, okay, we should get back to working on supernovae, and the supernova actually conformed pretty well with what we had predicted. In fact, we had written a popular view of it, and had pretty well everything pinned down, but this was something new and exciting, and so we jumped right in with everybody else. And here was the supernova in the Large Magellanic Cloud. On the left is the star where it was to begin with, and on the right was the supernova, and that was, well, sort of at the edge of our galaxy. And so we thought, okay, so now soon we will see a neutron star. And so we waited a while, and we went to Caltech every January, and we asked the observers, when are we going to see the supernova? And the observers, whatever year we asked them, said, well, it will be in another year. Now, in fact, we waited about 3 or 4 years, and still there was no pulsar. And every year we asked the experimentalists, when will we see a supernova? They said, well, there's a lot of rubbish there, and that has to clear out. And so said, how long will that take? And they always told us that will take a year, at least another year. So we actually decided that that was a time constant, that it was always going to be 1 year. And then I remember that I called Hans up on the phone one night and gave him the reasons why the star had gone into a black hole. And he gave me all sorts of reasons why it had not. About an hour later, my wife called me to the phone and said, Hans wants to talk to you. And then he said, you're right. And in the meantime, I'd worked out with a graduate, with a student here, that if there had been a neutron star there, then it took the matter about 1 year to clear out. And having cleared out in the 1 year, then one would see the neutron star with and intensity sort of Eddington accretion, because the matter would accrete onto the neutron star. Now that was in 1994, and the paper was not generally accepted because it used hypercritical accretion, but that actually turned out to be something that we believed in and used in many of our calculations. So the point is that he then changed over to working on black holes. Now, the next year we went to Caltech, and just that was the year that he became 90, and we went to Caltech. And just the week before we left, Kip Thorne at Caltech, who was a great expert on black holes, said to us, you people seem to be better at calculating things we don't see than other people. Could you calculate the number of binaries that we would expect in LIGO, that is the long interference, and because we were measuring them, long interference gravitational laboratory. So I said to Hans, okay, so we can calculate them next year when we come back. And he said, oh no, I would like to begin right now. Can you send me a review of people who have calculated these black holes? Well, I knew there was a review from Holland by men called, one of the world's greatest evolvers, a star Vandenheuvel, and I said, okay, I will send you such a review. So I sent him the review, which is actually about 34 pages long, and we were home by then, so I got a fax from him saying, now, it was 2 pages long, and the fax said, I seem to have got about the same answers as Vandenheuvel, but probably they're not as accurate because it's only 2 pages long. Well, then he was 90 years old, and he really plunged into the matters, and we wrote a paper together on black hole, well, compact object binaries, especially black holes and neutron stars. And in this paper, we used this hypercritical accretion, which the astronomers did not believe in because it was many times more than the maximum accretion that they had, i.e. Eddington. So then the next year, I was explaining to him what our work had been in 1994 about showing that 1987A had gone into a black hole. And this was at breakfast time, and I told him about the accretion and the hypercritical accretion. And then at breakfast he said, I think that I can work that out. And in fact, he had written a paper on stopping power, which was actually the second or third large paper that he had written, and he thought that he considered that the best paper that he had written. And this is sort of peculiar given the Bethe ansatz and given the Lamb shift and given the burning of stars for which he got the Nobel Prize. But he in fact liked that paper best of all, and it turns out that that paper is really quite similar to accretion, which I didn't know at the time. I mean, the way that it's phrased is completely different, but after the breakfast, we went to the office, and at the end of the day, I found out that he had solved the accretion problem on one sheet of paper. And now what was amusing about it is that people had begun calculating accretion on large machines, and accretion or the common envelope evolution, which is a sort of technical thing, but common envelope evolution had taken 10,000 years when done in 3 dimensions, then 100 years when done in 2 dimensions, and 1 or 2 years when done in 3 dimensions. But he of course, actually in what he had done, he had an analytic solution and he couldn't tell how long it took, but he'd solved the whole accretion problem, and we still have it today. In fact, there by now are a number of proofs that hypercritical accretion does take place, but this becomes somewhat technical, and I won't go into that. Well, with 97A, he had done a first calculation which I wanted to show, and that when it went off, he simply sat down. I mean, this is the way that he worked. If he wanted to understand something, he immediately took out his slide rule, and then the HA beta way was to calculate using the simplest possible model with his slide rule. And on top of that, and the most important part of the HA beta way of calculation is to not let anybody tell you that the situation is really much more complicated than what you've chosen, the simplest possible one. And there, the first day of the supernova, he had calculated that there should be only about half of a neutrino detected. This turned out to be the same as Adam Burroughs, who now just became professor in Princeton, got. Now, if I take 1987A, well, then I have accretion shock. This is sort of also his work, and then a shock going out. And I'll be somewhat brief in these because they're fairly technical, but matter would fall back on the neutron star, and the material on the accretion shock would, and then I have the full common envelope evolution, which I discussed, which is that neutron star running around another star induces a tidal distortion, and then sort of drags it around, and ultimately the objects fuse. And in 1998, we showed that the common envelope evolution can be carried out analytically following our breakfast together, where he'd seen that it's like the problem that he'd worked with the stopping power. This is, and then, now the way that he worked was that he actually could put down the relevant equations, and this is the common envelope evolution, which he'd done on one page, and he actually just used standard equations like Kepler. I won't go into great details because of the audience, but the point is that when he came to the last equations, he actually had two variables, m sub a and y equals mb, the second star, and he had only, he had two equations, but there were three variables in the two equations, and he set the star m sub a, which would become a black hole, equal to 0, which reduced it to just the two equations and two variables, and then he knew that he could solve this analytically. So this is the solution, and basically he showed in the solution that if the two black holes, sorry, if I start with a double neutron star, then the second born neutron star would always go into a black hole. Now, I had actually shown earlier there was a special circumstance that would stop it from going into a black hole. So, in fact, the special circumstance is that if they burn helium at the same time, you don't have to go into a black hole. And this shows that the lower band on the star is the companion, and then the pulsar is written just above it, and that we've now shown that in fact all of the double neutron stars must be within 4% of each other in mass, or they would go into a black hole. This is something that I was discussing with him. So this meant that in fact when we were through, most of the originally double neutron stars became black hole neutron stars, and this is still being argued about, but we were discussing and actually talking a lot with LIGO our last times in California. So then we had I was walking with him on a Saturday. We went walking on the weekend usually in the hills around the Caltech, and I was telling him about Kaon condensation, where when the stars get to be, neutron stars get to be large enough, they will collapse into a Bose condensate, and he immediately made the connection and said, "You mean you're squeezing electrons into K- mesons?" And this came actually quite early, the first paper on that, and we published a paper saying lots of black holes in the galaxy. Now, this also is still being debated, but and we don't have any results from LIGO yet. This is the Kaon condensation. And so we came to work on black holes, and we could work out, we wrote a paper in the year 2000, which was the last seminar that he gave at Caltech. And in this paper, we worked out what he called a theory of gamma ray bursts. Now, won't go into a lot of detail, but the point about this theory of gamma ray bursts is that we actually were powering them by using the rotational energy of the black hole as a central engine. Now, this followed something called the Blandford-Znayak theory, but it is maybe a bit complicated, but the black hole has a lot of rotational energy. In fact, something like 10 to the 54 ergs. And so in stopping partially, it can deliver its energy to its rotational energy to the gamma ray burst. And we were actually able to make an analytical calculation of this. In fact, it's more or less like a Prius when it goes through town. Namely, with the Prius, if you come into town, then the rotational energy of the armature is large enough so that the motor will turn off, and then the armature will continue taking the car through the town. So since then, we've been able to make the theory quantitative and have been publishing papers on it. But I remember that he gave a last talk in Caltech, and in fact he was, the year 2000 was the last one, but in 1998 he talked about the neutron star black hole binaries in front, and of course the whole of the auditorium was filled, and then he just stood up, he's standing tall, and using transparencies, and as he took each transparency out, there was a general gasp from the whole audience because he was able to make the solution of the various equations, and the audience, who mostly came from the caves beneath Caltech and their computation, could hardly believe that one could do all of this analytically. So I had really the opportunity to work with him for 21 years, a little bit more, and we wrote this book, The Formation and Evolution of Black Holes in the Galaxy. A lot of it was not read at that time, but more and more of it is becoming checked by observation. In particular, the Kerr parameters of black holes are being measured by a Harvard-Smithsonian combination, and they come out more or less bang on. Well, I had worked with Rudy Peierls for many years. Rudy Peierls was Hans's best friend, and when Rudy Peierls died, I phoned Hans, and he phoned back, and he said, well, a large piece of my life has been taken away from me. When Hans Bethe died, also a very large part of my life had been taken from me. So thank you.